So, welcome officially to the final exam review. We're going to cover all of the really big stuff, not everything ever, just because it's a lot of stuff. So we're going to try to get through as much as we can in the time that we have. And someone asked, when will yesterday's SI session be on YouTube? It should be there. I'm not sure why it's not, so I will check on that right after we finish. And I will try to upload this one tonight, or if it doesn't process by then, I'll do it tomorrow morning. Okay. So, chapter 9 felt like a really long time ago, so let's breeze through it really quick. A lot of this stuff that I have in this handout was also in the other handouts throughout the semester. So some things I'll tell you, I'll make a note of it and tell you to look it up from your handouts or from the past videos. And if you have questions, you can always email me. And yes, the last hour we are going to be going over a packet of practice problems. So the first 2 hours is going to be concept. The third hour The third hour will be practice problems. All right, so I figured we would start all the way at the beginning because it has been a hot minute since we did NMR. So basically, NMR, it has to do with magnetism, spin states, things like this. So all you have to know for how it works is that you have a magnetic field and spin. And you're going to measure the frequency I know it's very, very simplified, but that's all you really have to know for this exam. You don't have to know everything. As long as you have a vague idea of what NMR is, that's good enough. And so now we're going to go through all the different spectroscopies that we've done this semester and very briefly describe them. So IR tells us about functional group. Whereas NMR tells us about the carbon-hydrogen framework, or you could also say the skeleton. Mass spec is going to tell us the mass, which can be used to find the formula. And UV spec is going to tell us the level of conjugation. So all of these things are giving us different information about a molecule. And we, when we're actually doing research or in a lab, you are pretty much going to be using all of these for different things. You guys say the nicest thing in the chat. Nicest things in the chat. I heart you guys if anyone has to go early. Okay. Sorry. I just didn't want to ignore the very nice comment. Anywho's. So the criteria to be NMR active is it has to have spin. I mean, not spin. It has to have spin. Which we can say in order to have spin, something must have an odd number of protons and or neutrons. We did a bunch of these examples throughout the semester, so if you don't know what I'm talking about, please go back and watch the Chapter 9 videos. As far as what solvent is used for NMR, we are using deuterated solvent, and it's more likely than not that I spelled deuterated wrong, but that's okay. And what I mean by that is we're using deuterium instead of hydrogen. The most common one is CdCl3. Something that people always mix up is the solvent and the calibration standard. So CdCl3 is the solvent. The calibration standard is TMS, which is tetramethylsilane, and it looks like this. And this is our 0 standard, aka very shielded. So that's the intro to NMR. The 4 aspects of NMR are number of signals, is multiplicity / splitting. And there were a couple things we talked about. So for multiplicity and splitting, we have to remember the n+1 rule. N equals the number of unique neighbors. And we also know the heteroatom rule. And the heteroatom rule states that you cannot split through a heteroatom. And the other one that's not really a rule, but it's like the defining characteristic of multiplicity. To be a neighbor, it has to be within 3 bond lengths. Number 3 is chemical shift. And chemical shift is just going to be something's position on the spectrum. And something's position on the spectrum would be in ppms. And we can also say that that tells us how shielded versus deshielded something is. Last but not least, we have integration. And all that tells us is how many H's or carbons there are per signal. Excuse me, I have the hiccups. One thing to note, this guy right here is only for HNMR. Multiplicity and splitting is not a thing for carbon NMR, only for hydrogen NMR. All right. So for counting signals, we've done examples like this. I'm pretty sure we have done some of like these exact examples, so we're only going to cover 2 of the most important ones. So first of all, we have something like this, right? And the importance here is, 1, we have to figure out what unique signal means, and we also have to keep in mind symmetry. So this example, I'm going to draw the symmetry as a red dotted line. So we have symmetry here, and we also have symmetry here. So we split this up into 4 quadrants, and all of those 4 quadrants are exactly the same. So this carbon is the same as this one, is the same as this one, is the same as this one. These 2 are the same, and those 2 OHs are the same. But we also, in addition to this kind of flat symmetry, we also have to keep in mind the fact that these 2 groups are both pointing upwards. So the top of the ring and the bottom of the ring are different, which means each of these carbons will have 2 separate signals. The blue one, aka the one pointing up, the wedge, all of those wedged hydrogens are the same, so we'll call that hydrogen 1. All the green ones, which are the ones pointing down, are going to be exactly the same, so that's number 2. These two purplish ones or pinkish ones are number 3, and this guy is number 4. So we're going to say there's 4 total hydrogen signals. And as far as carbon signal goes, it's pretty straightforward because there is only 2. Practice this one on your own. The only difference is it's trans instead of cis. So now we are going to look at the cyclopentane and the cyclobutane. Dr. West really likes these examples. I'm sure you probably saw it on exam 1. And I have one trans example and one cis example for you. So for the cyclopentane, we can see in 3D how some of them point up, some of them point down, and we have one methyl pointing up and one methyl pointing down. So what we see is even though they're pointing opposite directions, there is still symmetry here because we can rotate, and if we hold this in place and we just rotate this thing, it will end up down here. So the short story here is this side is exactly the same as this, which would make this hydrogen exactly the same as this, which means the top environment and the bottom environment are exactly the same. So now this up and down facing hydrogens are not different. Unlike the last example, they're exactly the same. So we end up having 1, 2, 3 hydrogen signals. And we have 1, 2, 3 carbon signals. In the cyclobutane, it's another cis example, so these methyls are pointing up. We can see they're exactly the same. And now the top of the ring and the bottom of the ring are completely different, which means these up-pointing hydrogens and these down-pointing hydrogens will be different signals. So we have 1, 2, 3, 4 hydrogen signals. Oops. And we have 1, 2, 3 carbon signals. I know I'm going through these a little bit fast. If you have questions, please do let me know. I do get through as much stuff as possible. Do the rest of these examples on your own, and the answers were in previous packets and previous SI sessions. I'm sorry, I cannot speak today. All right, so when we talk about signal types, this was something that was really hard for people to grasp at first. I'm sure you forgot about it, but hopefully it's easier to catch it again now. So homotopic, heterotopic, enantiotopic, diastereotopic. All you really need to know, homotopic equals the same. Heterotopic equals different. So remember, these two terms are umbrella terms. Enantiotopic and diastereotopic are specific types of homo or heterotopic signals. So we'll start with enantiotopic. Enantiotopic signals are the same, and they only occur on potential chiral centers. And we know that a potential chiral center is something like this, where there are 2 hydrogens present and 2 unique groups. So if one of these hydrogens were replaced versus the other one, you would get 2 enantiomers. So you would get R or S. However, diastereotopic is different, and that occurs in 2 different ways. So it's either chiral center present or on a double bond. So what that looks like is Also, I see that my screen is a little bit slow. Is my voice choppy or anything, or are you guys able to hear me and see me clearly? Let me know while I draw this out. Okay, someone said I'm good, so I hope that is the case for everyone. Okay. So in the case of a chiral center, we know that if there is one chiral center present, every other potential chiral center will be diastereotopic. So this is the potential. This one is the real chiral center. And so these guys have to be diastereotopic. Whereas in the double bond, there's a couple things you have to look out for. So when you have a double bond, you're going to cut it in half. The left side, or side A as I like to call it, has to have 2 unique groups, and side B has to have 2 hydrogens. If you have 2 unique groups, 2 hydrogens, these guys are diastereotopic. And yes, to recap the chirality one, you need a chiral center plus a potential chiral center. Exactly. So chiral center plus potential chiral center. If I had something like this, side A and side B has 2 hydrogens, so that checks out. But side A is completely symmetrical. So that means these guys are homotopic. And last but not least example, I'm going to move this guy over a little bit. So if I have something like this, we have side A and side B. Now we have 2 unique groups and 2 hydrogens, but they're not on the right carbons. So these 2 hydrogens are on 2 completely different carbons. So they would be heterotopic. And they're just completely different. So, bam. Now, chemical shift equation, if we remember, is just ppm equals hertz over megahertz. And so we can basically solve all of these with straightforward algebra. So, for example, number 1, we have ppm and we have megahertz. So I'm going to put an x here. All we do is multiply 400 times 1.25, and we get 500 hertz. And you know what? I'll go like this just so you kind of know what I'm doing. In equation or example number 2, we have no ppm. We need to find that. And we have 1307 hertz over 180 megahertz. And so if we do our little algebra, we get 7.26 ppm. So these kind of questions should be very straightforward. You don't even really have to think. Just remember ppm equals hertz over megahertz, and you should be good. All right. So as far as chemical shift regions go, this tends to take a lot of time to talk about. So I want you guys to go through and fill this out on your own. I'm just going to tell you the most important things. And it should be in the exam 1 cheat sheet, so I'm not leaving you with nothing. The biggest takeaway from here that I want to talk about is the carbonyl region. So the carbonyl region in HNMR versus CNMR is very different because in HNMR, obviously, we're looking at the hydrogens. In carbon NMR, we're looking at the carbons. So in HNMR, I'll zoom in, we can look at resonance as being pulled far away from the hydrogen. So this guy is extremely, extremely, extremely deshielded. And then this guy is also deshielded because that resonance is going up, but that resonance is way, way less strong than this one. So this is going to be more deshielded. So this will be at approximately 12 ppm, and this will be approximately 9 ppm. And then we have our lovely ketone that we can't forget about. So a ketone is actually in the alkyl region because remember, any hydrogen that's attached to a carbon that's only attached to other carbons and hydrogens is always in the alkyl region. But this is a little bit higher, so this is around 2.5 ppm. So it's pretty high for the alkyl region. However, in the carbon NMR, we can see that we definitely do look at resonance. So I will draw resonance really quick. There's no resonance for the ketone. Really, besides that. But even more than resonance, we observe something called electronic effects. So electronic effects are basically describing how this carbon density is donated from each CH3 to here. So those carbon groups are going to donate electron density to that delta plus. So what this means is this is going to be less positive, aka more shielded, the more donation there is. So what you might not see at first is this resonance is actually donating to this carbon because the resonance will be going like this between those two atoms. So it's technically donating here. So this is going to be the least deshielded of the bunch. So it's the most shielded. So we're going to say this is around 90, I believe. Whereas this guy is getting the least amount of electron donation. So this one will be around 120. And our lovely ketone will be somewhere in the middle, so let's say 100 ppm. So I'll zoom out so you can take a look. I know we went through that super fast. Does anyone have any questions? Alrighty. So as far as spin-spin splitting goes, please don't confuse this with having a spin state. Spin-spin splitting simply means a multiplicity higher than 1. So anything that's a doublet or beyond. So let's see here. We're looking for at least one hydrogen that's not a singlet. So these guys, they have 0 neighbors because 1, 2, oopsie, there's a heteroatom. You can't go through that. So this is a singlet. This hydrogen, however, is 1, 2, 3 bond lengths away from these hydrogens, which means it does have neighbors. To be exact, it has 3, 6 neighbors. So this guy is a multiplet, and it does show spin-spin splitting. However, the second guy right here has symmetry down the middle, which means this and this are exactly the same. Since they are the same hydrogen, they cannot split one another. So no, this one does not show spin-spin splitting. Lastly, we have this guy, and he's kind of similar to the first one that we did, except now there's no hydrogen here because it's completely substituted. So this H and this H cannot reach each other. 1, they're too far apart, and 2, there's an oxygen in between. Therefore, this cannot have spin-spin splitting. Okay, so I did draw out a little J-values section, but there's really nothing to J-values. It's just a bunch of memorization. So please see the Exam 1 cheat sheet and fill out these numbers and just kind of try to remember them. I do want to spend a little bit of time on normal splitting versus complex splitting. So if you guys remember, normal splitting follows the n+1 rule. And we know n is the number of neighbors. So let's say we're counting for this guy. The way I have drawn it, it has symmetry, so I'm just going to add an extra carbon here. So don't be confused, I just added a carbon here. So for the red hydrogens, we are going to count the number of neighbors. So there are 1, 2, 3 blue neighbors, plus we have 2 neighbors here that I can draw out in purple. Plus 1. So this guy is a triplet. And then if we do this for the blue hydrogen, we see that these blue hydrogens have 2 red neighbors. So we have 2. Plus 1 equals... Oh, dude, I'm so sorry. This is clearly not a triplet. I was thinking about this one. So this one is a triplet. This one is 3 plus 2 plus 1, which is 6 if you're not completely oblivious to the world. And this is a sextet, whereas this guy is a triplet. I'm very surprised nobody pointed that out. I'm just really not here today. I apologize. Okay, so complex splitting is a little bit different. Now we do n+1 times n+1. And so let's look at the red carbon, or the red hydrogen again. So we see that the red hydrogen is sp2. This guy is sp2. This one is sp3. So the value between this and this is different. So we have different J values. And that means that we have to do complex splitting. So I'm going to do a little red multiplication sign so you know which one we are looking at. We're looking at the red hydrogen. And on the left side, we have one blue hydrogen plus 1. On the right side, we have 2 green hydrogens plus 1. So we get 2 times 3, which is in fact 6. But it's not just a sextet this time. It is actually a doublet of triplets. And that's something we call complex splitting. All right, the last part of NMR that we're going to talk about is 2D NMR. So this stuff is pretty straightforward. All you have to know about 2D NMR is that COSY is HH correlation. The way I remember it is you're just looking at 2 hydrogens that are next to each other. So those hydrogens are nice and cozy with one another. So since the hydrogens are nice and cozy, we're going to use the COSY technique. Det is distortionless enhancement by a polarized transfer, blah. So it is giving you the in-depth info on CH3 versus CH2 versus CH. So it's telling you more about the carbon-hydrogen attachment, whether it's a CH3, CH2, or CH. Last one is het core, and that is heteronuclear correlation. Just know that het core stands for heteronuclear correlation. That's as far as you need to know for that one. All right, so we are done with NMR. Yay! That was the fastest we've ever gone through NMR. If you have any questions, please do let me know. But we're going to whiz right past mass spec. So how mass spec works is we have a molecule, and for example, I'll give you something like this. We put it into the machine, and the machine is going to fire a beam at it. So it fires a beam. And that beam is going to cut off different fragments of the molecule. And we get this plus this. We also get a whole bunch of other things because we're going to break all of these bonds and crush it and all these kind of things. But this would be the most stable. So that's why I drew it to you like that. All right. So the base peak is actually going to tell us a little bit more information about this guy. Because as I told you, that's the most stable radical. Or the most stable fragment, we can say. And this is going to be the tallest peak. And it will be close to 100% absorbance. Next up, we have the M plus peak, which is also called the parent peak, which is also called the molecular ion. And this is the mass of the unfragmented molecule, aka total mass of the compound. So the M plus 1 and M plus 2 peaks are just two peaks that come one after and two after the M plus peak. So that's why they're named like that. So the M plus peak is going to tell us about carbon, hydrogen, and nitrogen isomers. This peak is always super tiny and is always, always, always present. And the reason for that is because in every single sample you ever do, you're going to get about a 1% carbon-13 trace. So you're always going to have a tiny M plus 1 peak. If you have a peak after this, that's the M plus 2, and it tells you that there is an oxygen, sulfur, chlorine, or bromine in your molecule. So if there's an oxygen, it will be a super, super tiny peak. I believe it's 0.10% the height of M plus. If it's a sulfur, it'll be a teeny tiny bit taller, so it'll be like approximately 10% the height. Now the really interesting one, so oxygen and sulfur you could find, but we don't really care. The better examples are chlorine and bromine. So chlorine is approximately 33% the height. And we can say that this is at a 3-to-1 ratio, where we have M plus 2, M plus 2. Bromine is approximately 100%, and that means it is a 1-to-1 ratio. So someone asked, so the M plus 1 is always next to the M plus peak or next to the base peak. So the thing here is that the base peak doesn't always have to be the M plus peak, but they can be the same. So the M plus 1 peak always has to be next to the M plus. It does not always have to be next to the base peak. Okay, you're very welcome. So fun facts, I just gave this to you because I didn't want to waste time like writing it in the exam review, and they are stuff that we've already talked about. So please just remember that the mass of bromine is not actually 80, even though that's what's written on the periodic table. Just know that we said we have a 1-to-1 ratio. All that means in reality is that in the real world, we have the same amount of bromine 79 and bromine 81. And the periodic table just does the medium weight, or excuse me, the average mass, I should say, which is 80. Also, if you have an odd number for your M plus peak, that means there is an odd number, of nitrogens present. So again, odd M plus equals odd number of nitrogens. Last but not least, in mass spec, if he says that we have a minus 17 or a minus 18 peak, he's always talking about a leaving group that is OH, because OH can either leave as OH or it can leave as water. So that would show you either a minus 17 or a minus 18 peak on the spectrum. I know that's kind of hard to grasp when you don't have a picture, so if you don't know what I'm talking about, please watch the SI session or the concept video on mass spec. Okay. I know that was pretty fast. We're done with chapter 9 now. Yay. I'm happy. We're kind of making good time. Any questions? All right. So let's breeze through chapter 11, which is alcohols and ethers. So I suggest studying 9 and 11 together just because they're the weird chapters that don't really fit into other things. So chapter 11 focuses on alcohols and ethers. So we need to know physical properties. We know boiling point is a physical property. And we also know that alcohol has a higher boiling point than an ether because of hydrogen bonding. That makes these bonds harder to break. And now when we're comparing different types of alcohols and different types of ethers, we need to consider something called branching. So the more branching, the lower the boiling point. The reason for this is the more branching we have, the less tightly packed we are. So if we're super, super tight like this, it takes a lot of energy to rip those apart. But if we're like this anyway, it does not take a lot to rip these apart, right? So this is going to be the highest BP to lowest BP. Sorry. Same exact thing for ethers. The more branching we have, the lower the boiling point, but now we have to watch out for the two different sides. So if we have something that has two sides with no branching, that's going to be the least, it's going to be the most tightly packed and the least branching. If we have something that has branching on one side and not the other side, that's going to kind of be like an intermediate. So it's not quite as branched as this one, but it is going to have a lower boiling point than this completely linear one. So we can still say that this is the highest and this is the lowest. One other thing that you should consider when you talk about boiling point is that the number of carbons you have present also determines boiling point. So if you have, a carbon chain that's like this versus this, yeah, of course, this one has to have a higher boiling point than this one because there are just much more bonds to break. If we have something like this, and yeah, this one has branching, and we know branching equals lower boiling point, but again, if we have a ton more carbons, we can assume that all of these carbons are going to make a huge difference. On the exam, he's not going to do something like this to you. He will definitely compare this with this and compare these guys. But just know that if you have an insanely long chain with one branch, that's not necessarily going to make your boiling point lower. Okay. So, acidity. We've talked about acidity a couple times this semester, so I hope it makes a little bit more sense than it did before the semester. But specifically in chapter 11, we are going to talk about alcohols and acid-base reactions. So this chapter says that alcohols are primarily weak acids, but they can act as bases. Sometimes, we're not going to talk about that right now, but you need to know that an alcohol, if it reacts with a base, will create an alkoxide, which is just the conjugate base of an alcohol. This comes up again and again in later chapters, so it is important that you remember that. The other part of this that you should know is ranking the order of acidity. So as we know, triple bonds are more acidic than double bonds, which are more acidic than single bonds. However, if something is bonded to an oxygen, that's much more acidic than if it was bonded to a carbon. So we know that C is going to be the least acidic, followed by A, because A has no resonance. B and D both have a lot of resonance, but if you draw these structures out, you will see that this has a charge on a carbon, whereas this has charges only on oxygens, and so that is much more stable, so it is more acidic. Now, when we talk about strongest acid versus strongest base, first things first, we know that this is an acid, and we know that this is its conjugate base. Excuse me, I drew it in the wrong spot. This is its conjugate base. So we also can assume this is a base, this is a conjugate acid. But if you didn't know that, let's think about logic. We know that anything with a negative charge is a nucleophile or a base. And so odds are these guys are our bases, which would make these guys our acids. So we're trying to figure out which acid is the strongest. So we're between this one and this one. And the question here has to do with electronegativity. So the more electronegative something is, the more tightly it holds on to its electrons and it doesn't want to share. So the stronger acid is going to be A, because OH is more electronegative. The oxygen wants to keep all of its electrons, so it's fine with letting this guy go, because then it gets all the electrons for itself. So this is the strongest acid. For the strongest base, we're going to use the same idea, but we're going to flip it around. So we want the least electronegative one to be a strong base, because the less electronegative it is, the more able it is to use its electrons. Like nitrogen wants love. Nitrogen wants that hydrogen. It's willing to give up some electrons for that hydrogen. But oxygen is fine. It's like, I'm chilling here with my extra electrons. I don't care about hydrogen that much. I don't want it. So we know that nitrogen will be the strongest base. I will leave that up for you for a moment. All right, so now we have protecting groups. So someone asked, isn't the strong usually on the right? So there's a bunch of different kinds of acid-base reactions. So the ones you saw in Orgo 1 and Gen Chem, usually it is written differently. But for Orgo 2, it's okay that they're on the same side and they're on the left. Okay. So, protecting groups. We know that PBr3 is going to act as a protecting group, and it's going to turn OH into a Br. And we know that it's going to flip the stereochemistry. We also know that in this second part, we do an SN2 reaction, which also flips the stereochemistry. So overall, we keep stereochem. Whereas mesylate and tosylate, they keep stereochem in the first step. They flip it in the second step, so we overall flip stereochem. So if you were to ask you a question like this, like match the correct reagents, we keep the same, so we know we had to use PBr3. Flip, we know we had to use mesylate or tosylate. So the answers here would be A, B. All right, so for dehydration of alcohols, all you really need to know is an acid-catalyzed dehydration is going to be an E1 mechanism, which means you can have rearrangements. POCl3 is going to be an E2 mechanism, which means one step, no rearrangements. That's all you have to know for this class. And I already drew it out for you. So just remember, acid-catalyzed, rearrangements, POCl3, E2, no rearrangements. When it comes to ethers and epoxides, we can break ethers and we can make ethers. We can break epoxides and make epoxides. So regular old ethers are stable in base, reactive in acid. And we know the order of preference of attack in acid is a pain in the ass to remember. So it's 3, 1, 2. And epoxides are super, super, super unstable. So there are reactive in acid and base. And so in acid, we are going to break 3, 1, 2 again because it's still a pain in the ass. But for bases, these guys are basic bitches, okay? Nothing complicated about them. So we're going to do 1, 2, 3 because that's as basic as it gets. And in case anybody doesn't know what these numbers mean, this is telling us the preference that our nucleophile is going to have to attack the epoxide. So it would choose to attack a tertiary side over a primary side over a secondary side. Okay, so when it comes to making ethers and epoxides, we know that we have the Williamson ether synthesis. And the Williamson ether synthesis is when we have a alkyl halide. Wow, I'm so sorry. We have an alkyl halide. We react it with an alcohol. We're going to attack, kick off the leaving group. And again, I'm very much simplifying this. But we end up with an ether. So we can say alcohol plus alkyl halide equals ether. We can do an intramolecular Williamson ether synthesis to make an epoxide. So what this means is we have OH and our alkyl halide on the same molecule. So this will attack, kick off the leaving group, and we end up... Why? I'm sorry. I drew too long of a chain. Let me fix that for you. So we're going to attack, kick off the leaving group, like I said, and we get an epoxide. The other way to do this is with a peroxy acid. And remember, peroxy acids are O3. So if I have a double bond plus peroxy acid, we end up making, yikes, an epoxide. And remember, if they are a cis double bond, you would get a cis product. A trans double bond, you get a trans product. last but not least for this chapter, we name crown ethers. So when we're naming crown ethers, it's always the bigger number, crown, small number, ether. So the big number is the number of carbons plus oxygens. Small number is just the number of oxygens. So we have 1, 2, 3, 4 oxygens. And instead of counting every single carbon here, we're just going to do 4 times 3. We get 12. So in this class, that trick is always going to work. We have 12 crown ether. 12 crown, 4 ether. In this one, we have 1, 2, 3, 4, 5, 6. 6 times 3 is 18. So we get 18 crown, 6 ether. Okay. That was a lot. We just went through 2 chapters and we went through them super, super fast. So please feel free to ask me any questions, comments, concerns, things like that. The first hour is over, so I'm going to end the recording and restart it, and I will give you guys like a little 2-minute break to grab a snack, grab water, go to the bathroom, anything like that. So I will see you in 2 minutes.